called Montgomery County. It is near Amsterdam, New York. The bridge was constructed in the year 1954, and it collapsed in April 1987, about 33 years later. And very interestingly, the bridge had, the flood discharge in this particular stream was maximum just a year after the bridge was constructed in 1954. In 1955, the flood design discharge was the highest that was observed. And at that time, this foundation of this particular bridge, there were a lot of protection work which was given at the time of construction. All these protections, many of
What is
the
the last
protection
thing?
actually got washed away during the first flood in
Sorry,
1955,
lastly interact అవ్వాలి కదా
and
6
it was to some extent repaired. But the second peak of the design discharge came in the year 1987, which led to washing away of the piers and this disaster. Uh, so let me go into the details of this particular bridge. Broad content, as usual, I will have these four sections as the content of my presentation. I will discuss about the structural arrangement and the span arrangement of the bridge which has collapsed. Then I will talk a little bit about its design and construction, and then the cause of collapse, and the last concluding will be the lessons learned from this collapse. So, as I was mentioning, that this is a five-span continuous bridge, not continuous, it is simply supported bridges, and the spans were in the range of 100 feet to 120 feet. 100 feet would means about 33 meter to 36 meter. And the initiation of the collapse started from scouring of pier number P3. This is pier number P3, and this is the first one which actually the pier failed, and because of the failure of the pier or washing away of the pier, the span 3 and span 4 first came down, and then within a certain period, span P2 also gave way, and even in span 1 also there were problems. This particular bridge is a part of the stream, particularly is a part of a a, a stream which comes out of the mountain. It's called a Catskill Mountain, and it goes the creek meets at the river which is called Mohawk River, which is on the downstream, and there is a barrage at the downstream. And I will show you some pictures to show that the bridge at this particular junction, where the stream at this particular junction has got a very steep curve, and one of the reasons for the collapse is said to be the curvature in the stream, because of which one side is getting more scour as compared to the other side. Uh, the it has the total bridge I mentioned about this. The total bridge length 165 meter, and it survived the 100-year return flood in 1955, which is just a year after the bridge was constructed. But the damage inflicted at the time might have caused eventually the eventual collapse in 1987, 33 years. This is the original general arrangement. At the time of construction, this was the general arrangement. So this is the original design plan, though it is called plan, but it is elevation. And as you can see, all the piers in this particular bridge is actually on open foundation, and it was very shallow foundation. You can see the depth of from the bed of the river, there was hardly any depth. And of course, the scour protection was done by using riprap, and there was some sheet piling also done in the two. You see, two out of these four piers are in the stream, and the other two are actually in land. But as you can see, the riprap protection was given in all the four piers. more in the pier number P2 and P3. And the abutments were on resting on pile foundation. You can see the piles in which we have the raker piles as well as the vertical piles, a group of piles which were there. This is the plan view of the original design, which shows four piers: pier number one, two, three, four, and it is a six-lane bridge, three-lane each way with a divider in between. So I think the arrangement of the bridge is quite clear, I hope. And the stream flows, you can see this particular bank of the river is actually in curve. I will show you some photograph. And therefore when the water moves from upstream to downstream, it actually gives more cover to pier number P3, and therefore it is understandable that pier P3 first sort of got washed away. This is the cross section of the bridge, which makes things pretty clear now. So what you have is a steel concrete composite deck on top. The spans ranging from 33-meter to 36-meter, five spans. And as was the practice at that time, most of the bridges at that time, you see, you have a girder. It's called a ladder type of composite structure, where you have two girders which are 57 feet apart, almost about 18 meters. And then you had these cross stringers, the cross stringers at every 2 meter, 20 feet, 20 feet center to center, and that means 6 meters. And then this is followed by longitudinal stringers, which are at every 8 feet center to center. So you have first a longitudinal beam, main supporting beam, through which the load is transferred to the pier, and then it is followed by transverse floor beams, and then it is followed by the longitudinal stringers, and on top of that the deck slab is there. Now this used to be the type of superstructure those days, not very economical. In today's scenario, if one has to do a superstructure, there will not be so many type of structures. Either there will be longitudinal with a deck slab on top, that is only two sort of action. One is the main girder and one is the transverse system. Here you have first the main, then you have the transverse, then it is further longitudinal, and then the deck slab. It is not a very optimized section, but that was the trend at that time. Now coming to the pier, you can see the proposed arrangement had two piers, two independent columns, and quite strangely, these columns were not vertical. They were having a inward inclination of 1:120. You can see, not visible through naked eye. It appears to be vertical, but it is not. And then there was a foundation, open foundation. The footing size was 19 feet by 82 feet. 82 feet is the transverse direction, 19 feet is the longitudinal direction. And then there was a this was very lightly reinforced plinth, and which subsequently cracked. I will tell you about that also. And these simply supported girders were resting on metallic bearings, rocker roller type of bearings. The pier frames were constructed of two slightly tapered RCC columns. RCC columns were fixed within lightly reinforced plinth, and the spread footing was protected by layer of dry riprap. This is what I mentioned to you. Uh, the as-built drawings for the bridge did not reflect the true conditions. You see, let me make it clear what is meant by as-built drawings here. You see, normally you have a design drawing based on which the contractor is supposed to carry out the construction. And then once the contractor constructs the bridge, there may be some deviations from the design drawings which he has to carry out due to some constraints, unforeseen circumstances or constraints, non-availability of a particular material, etc., etc., or a site, a situation which is quite different from the from what was envisaged at the time of design. So, in any project, you will have a design drawing based on which the contractor is supposed to work. But once he completes his work at site, he is supposed to prepare as built drawing. That means the as built drawing will be nothing but the design drawing with changes which he has worked out, clearly marked there. And after failure, it was found that the as built drawing of this bridge was not the true representation of what actually happened or what actually was there at site. For example, the design drawing indicated sheet piles along with the riprap, and the as-built drawing also indicated the sheet pile. However, these sheet piles were actually not there at site. Apparently, it was there, it was removed after construction and taken back by the contractor. There were other problems encountered within a year of construction. I mentioned about it that the immediately after within a year there was a 100-year return flood with design discharge much higher than even the one which led to collapse in 1987. Uh, at that time itself, within a year, the concrete foundation, the pier plinths began to form vertical cracks. These cracks were ranging from 3 to 5 millimeter, and it was soon realized that there was insufficient reinforcement and the design was not correct as far as the foundation is concerned. And there were some problems due to which cracks occurred, and it was rectified, and some reinforcement was provided on top of the plinth to circumvent the situation. Though it was later found that even this added reinforcement was not detailed properly, not embedded adequately in the plinth. Now this shows the arrangement of riprap and the sheet piling which was there in the original design. You can see that this riprap arrangement, the top of the riprap was about 279.5 feet, and the bottom of the footing elevation is 270. So riprap was provided for a depth of about 9.5 feet, which means about 3 meters. Uh, uh, at PRP3, the thickness of the riprap was reported to be approximately 9.5 feet. This is so. These are some of the sketches, photo of the PRP3 taken. This was close to 1955 when this photograph was taken, though it was taken from a NTSB report of 1987 post collapse. But these are photographs of the original construction. The bridge actually collapsed on April 5, 1987, and that was after a record rainfall of about 6 inches, 150 millimeter in that area. And the first pier which got washed away is P3. You can see this photograph which shows how this is the upstream side of the bridge, and this is pier P3, this is pier P2. So you can see that when there is a flood, design discharge is high. This is the portion which is affected first, and once this pier P3 got tilted and the span two spans, span P3 and span 4, they came down. That blocked the area here, and that further led to subsequently collapse of pier P2. And furthermore, after 2 hours, there was some large distortion shown or seen in a P1, pier P1 and abutment. You can see this particular span is slightly tilted. So these are some of the photographs taken in April 1987, just after the collapse. And you can see these are at various stages of the collapse. This is PRP2, which is still existing, but then in the subsequent photograph, you can see that pier is missing. So this span is also gone here. You can see here all the end span is still existing here, and this is the final shape as it stabilized subsequently. So you can see this span one, which has not collapsed, but it got tilted because of the tilt in this particular pier. So, and what you see in the bottom, right bottom is the cracking in various piers, which was post failure investigation revealed that all the piers had similar cracks, which indicated that on one side of the foundation there was a lot of scouring, and which led to basically tilting of the plinth. These are some other you know uh, photographs of the collapsed bridge. You can see in various pictures you will get different dimensions of the collapse, and different you will get different ideas. For example, if you see this particular uh, photograph, you can see all the piers are cracked because of this cover here. You can see the cracks here, and you can see also the superstructure deck, which is lying on the bed. This is pier P2 and P1. P1, P2. The span. This is span. I think P2. P2 span P2 span two. So span two, you can see how it is because of the tilting of this particular pier. What is the scenario? Uh, these are other some photographs which which gives you uh, how the flow has affected this particular bridge and how it has affected other piers. And post collapse investigation, the consultant has given various sort of details, graphical details of various piers in the cracked position. You can see pier P1, this is the state, pier P2, pier. So this gives you an idea as to after the collapse, what kind of work is required to be done by the investigating structural engineering consultants to sort of take stock of these situations, so that the diagnosis of the and the analysis of the reason for failure can be done properly. So you got to map all the features post collapse, and also try to collect all the informations pre collapse or during, right from the construction, how it has right from the design, initial design and construction. All this information needs to be collected and collated to get a full picture of how the collapse occurred. So this is the I would say a drawing prepared by the forensic investigating agency, depicting how the collapse spans are there at site. You can see it shows position of the piers, how the pier foundation is broken. Each pier is marked here. Each spans in the collapse position is sort of identified here. So this is the kind of work a forensic investigating agency is required, expected to do. These are the actual real drawings of the expansion joint bearing and the fixed bearing, which is there in the bridge, which was there in the bridge. So these are all the bearing drawings. So I have discussed about the general arrangement, structural arrangement of the bridge, and in its how it has collapsed. Let us go into the details of its construction now, design and construction. The bridge was originally, the bridge was designed by a consultant by the name Madigan Highland Consulting Engineers. They were first engaged by the New York State Department of Public Works, DPW in short, and they were first engaged to give alternative preliminary design. And these consultants had given two alternative design. one with 600 foot bridge length and another with 540-foot design length, that is 165-meter. And the New York State Department chose the alternative, which is having a bridge length of only 540 foot, that is 165-meter, the one which I described, having five spans, with span length ranging from 100 feet to 120 feet. And final design was submitted in January 1952 uh, with 165-meter bridge length. The construction contract for this bridge was awarded to a firm by the name Messrs. B. Parini and Sons, and the construction started in 1953. During construction, the construction inspection was performed by the same consultant who was engaged for doing the detailed design, that is Madigan Highland Consulting Engineers, and they did the inspection work, construction inspection work and supervision in conjunction with the authorities, that is NYSTD, New York State Department uh, of Public Works. And I mentioned about this as-built drawing not reflecting the true bridge condition. And I also mentioned that within a year, there were some rehabilitation done, and the tensile, because of the cracks ranging from about 5 millimeter also, there were some strengthening done. But the unfortunate part is this plinth tensile reinforcement was only provided from the inner face of the pier to inner face of the pier. Obviously, they would not have, broken the pier and put proper anchorage of this reinforcement. They could have done by some other means, but naturally this reinforcement was not effective in some portion. So therefore it could not have solved the problem in entirety, though it helped to some extent to relieve, to give the relief. Now, several other problems also occurred shortly after the bridge was constructed. For example, the expansion bearings were found to be out of plumb. The roadway approach slab found to be settled due to poor compaction of backfill. The roadway drainage was found to be poor, and the supporting material for the west embankment pavement was found to be deficient. But none of these actually listed here uh, can be considered as the reason for collapse. But since the investigation team has had to go through each and every part of the reports of the inspection that has been carried out since its construction till it collapsed, so all these things came into limelight that there were many deficiencies uh, uh, in this bridge right from the construction. So now coming to the cause of collapse, as I mentioned, the cause of the collapse was basically the scour because of the inadequate protection given to the foundations. Even the original design was later found to be inadequate. The consultants even questioned the wisdom of providing open foundation in this case where this cover was expected. So while the abutments which was on dry was on pile foundation, while the piers in the stream which were vulnerable to scour are on open foundation was also questioned. There were two teams which investigated this particular bridge failure. One was Wiss Jenny Ilsner, that is WJE Associates, and they with uh, Mosier Rutledge Consulting Engineers investigated on behalf of NISTA, that is, New York Schoharie uh, Transport Authority or something like that, and Thornton Tomasetti. I hope you people remember this name, Thornton Tomasetti, because they were the consultants also carrying out the forensic investigation for the Hartford Coliseum roof collapse, which I sort of discussed in my last lecture. So they investigated for the New York State Disaster Preparedness Commission. I mentioned in one of my lecture earlier that when there is a failure, it is not one agency who generally do the investigation, because there are many stakeholders and every stakeholder will have to sort of you know, take care of their own interests, and therefore they independently engage forensic investigating agency to sort of look into the whole cause of collapse and try to protect their interest. So a team of experts also from another agency called Hudson International Group were involved immediately after the collapse to determine the cause, estimate the damage and cost of repair, and to recommend methods. So there were three, you can see there were three agencies involved in the investigation. So Thornton Tomasetti found six reasons that aggravated the tendency for scour. First, the flood was greater than anticipated by the designers and followed the 1955 flood and others that had disturbed the riprap. In fact, this 100-year design flood was also much higher than what they anticipated at the time of design. Uh, a curvature, a steep, sharp curvature in the river upstream of the bridge directed a higher velocity flow towards pier number 3. You see, the velocity was estimated at the time of scouring and the failure. The velocity was estimated to be around 5 meter per second, about 4.7, 4.8 meter per second, which was considered to be very high. And in fact, the riprap also was found to be the diameter of the riprap stones were found to be grossly inadequate for this kind of velocity of flow. The drift material caught against the piers directed water downward at the base of pier 3. The berms built in 1963 directed floodwaters under the bridge. So there were some berms which were built in 1963 just a little upstream of the bridge, and those berms actually, directed the floodwaters further into this part of pier P3 in that area. An embankment west of the creek channel increased the flood velocities, and the Mohawk River Dam downstream was set for winter conditions and was 3 meters lower than the 1955 flood, increasing the hydraulic gradient. So, this is another reason attributed, because that increased the hydraulic gradient of the stream as compared to even the 100-year return flood. Though the flood discharge was less in 1987, but the hydraulic gradient was more. Furthermore, this agency found a number of other factors that contributed to severity. Though these are just routine matter, I don't think that would have caused the failure, but they might have simply added, this is an added factor. For example, it mentions that the bridge bearings allowed the span to lift or slide off the concrete piers, which means there were no anti-dislodgement devices in the bridge. But let me tell you, those period when it was constructed, concept of anti-dislodgement device was not there. It is only a sort of present day we are talking about this anti-dislodgement, anti-seismic devices. I don't think it was there at that time. The simple spans were not redundant because these were simply supported structure. Their redundancy was much less, and it is now, on a hindsight, one can say that had it been a continuous structure, probably even if one pier got washed away, the complete collapse could have been sort of avoided. The lightly reinforced concrete piers did not have enough ductility to permit frame action. Yes, that is another reason why this failure took place suddenly. And in fact, the pier and its foundation was giving problem right from the first year of construction. The plinth reinforcement stopped the hinge action of the plinth cracks, and therefore, instead of dropping slowly into the scour hole, the plinth cracked suddenly. Because of the lack of reinforcement on the top, there was a sudden failure, because even the scouring was about 2.5 to 3 meters on one side, it was later found. The first two elements were common practice when the bridge was designed. Yes, the NTSB conducted its own investigation and concluded that the probable cause of the accident was failure to maintain the riprap. The bridge design originally called for leaving the sheet piles, which were used to keep water out of excavation area during construction around the piers. The specified riprap would then fill the area left between the pier footings and the sheeting. Unfortunately, the sheet piles were not left in place. Possibly, they could have prevented this cover altogether. Subsequently, and this is another important thing which they found, that subsequently, in the contract issued in 1980 for maintenance work, all the reference to new stone riprap had been deleted by the non-engineer state employee who decided after viewing the site from shore that it was unnecessary. So you see, it was true that the as-built drawing showed sheet pile and it was not there, but not that the authorities were unaware of. But when 1980, when they issued the contract for maintenance, they removed even the need for having that sheet pile from the maintenance work. All the references of the new stone riprap was deleted. So it was at that time thought by the person who took the decision in the contract to do away with the riprap altogether. So since the bridge survived for 30 years after the 1955, so they thought that so riprap is not necessary. We can do manage without. The National Transportation Safety Board determines finally that the probable cause of the collapse of this Cohery Creek Bridge was the failure of the New York State Thruway Authority. That means the blame goes to the authority to maintain adequate riprap around bridge piers, which led to severe erosion in the soil beneath the spread footings. Contributing to the accident were ambiguous plans and specifications used for construction of the bridge, an inadequate NISTA bridge inspection program, and inadequate oversight by the New York State Department of Transportation and Federal Highway Administration. So, in fact, one of the reason which they found is attributed to the failure was regular, though they were inspecting the bridge regularly, but nobody inspected the condition of scour or the condition of riprap, and therefore the inspection report did not have any reflection of the scour patterns and the vulnerability of these foundations to scour. That was not reported at all. Every inspection report focused on the condition of superstructure, condition of substructure, and condition of bearings, etc. So I have a video of the collapse. I don't know whether I should be able to. I think I should be able to run this.
Portions of the Cohery Bridge continued to fall hours after it initially gave way. The collapse sent cars and a tractor-trailer plunging into the raging floodwaters below. Just how many lives and vehicles were lost remains unknown.
We have one witness that tells us 4 cars, 1 tractor-trailer. We have another witness that tells us 1 tractor-trailer, 1 car. Lightning struck when the bridge went out, and then it just collapsed from there.
Witnesses say it was all over in 15 minutes. The eastbound lane went first. For the drivers of these trucks, it was a very close call.
It crashed me out when it went down.
Plenty of police and rescue crews arrived ready to help, but the waters were moving too quickly, and the risk was too great. All they could do was clear the area of traffic and keep the curious a safe distance away. The governor arrived to survey the damage and watched as still more than 400-foot span down.
We don't know exactly what caused the collapse of the span. Everybody be very cautious. See? The regard is something to be avoided for the time being. We're going to avoid it. Now, there'll be a lot of unhappy people, and there'll be a lot of detours, but so be it.
All of the other bridges along Schoharie Creek were closed since 6 a.m., including this one at Mill Point, which appears ready to give. Residents here want to know why this bridge wasn't also closed down.
If there was any thought whatsoever that this bridge was in danger, this road would have been closed.
Okay, so you could see the collapse of the second, the second span, not the first one. Yeah. So you can see this is the animation of, or this is just one animation of how the third span collapsed. Third span is span number 2, which is between T1 and T2, how that collapsed. Uh, I have another one. I will try to run this also. Let me see.
Calling. Get us some help down here. I don't know. I'm heading for the tractor trailer. Just went off the Schoharie Bridge. You're calling the 4 cars? Available. I have a tractor trailer and 4 cars. Schoharie Bridge just collapsed. Request all possible assistance. Tractor trailer evidently has gone off eastbound lanes of the Thruway through the bridge into the creek. They don't know if there's anything else or not. I got some debris floats down here. WNDH 650 clear. 49. Dark 1004, evidently the box has come completely open. I have a lot of paper product floating down through the creek. 28, please. Michael, Tom, Frank, 287. Thruway closed immediately by the bridge on 5S to see if we can rescue anybody. You read, Fonda? 6 copy. 6 survey. Article 1. The Thruway bridge collapsed over the Schoharie crossing. Somebody down the Thruway. Track 2, we're heading up back to our location. We'll run right over there.
Okay. So, so I think I think these two videos would have made things little clear about the collapse, how it has happened, and also some human angle of the tragic, catastrophic failure. Some 10 people died in that collapse, and some 15 people were injured. So, what are the lessons that we learned from this failure? The collapse of Scolari Bridge provided essential information on the design methods to resist cover and appropriate methods for bridge cover inspection. Many ways in which this collapse could have been prevented. The bridge could have been supported on pile foundation, which would have easily resisted this cover. Sheet piling could have been left in place, and more riprap could have been provided to protect the pier foundations. A continuous span could have been provided, which would have helped to prevent a collapse due to added redundancy. Another important lesson that is learned is that appropriate and frequent inspections be carried out on all aspects of the structure, including the underwater features of the bridge. During the bridge design, it is not only the dead load and live load that is important for design. The scour, the hydraulic forces, the scour depths are very, very important considerations too. And it appears that this part is taken a bit lightly by the designer, uh, because the kind of protection for scour appears to be very scanty. This Koheri bridge is also a reminder of why we need regular inspection and maintenance of the bridge which crosses our waterways. What are the changes to engineering and management practices? When the bridge was built, you see, the tools of the day were not adequate in prediction of scour. Today, we are in a much better position, and I think the techniques for inspection of scour and prediction of scour, this has improved leaps and bounds. So we are in a much better position today to sort of take a very safe and very reliable scour depth calculations we can do now. While the bridge was in service, the inspection procedures used were not sufficient to detect the scour. Today, in the inspection reports, the formats, the concern for the scour is also addressed pretty well. Since the collapse of this Koheri bridge, important advances have been made. A study conducted in 1989, subsequent to this collapse, there was an all over US study was conducted which revealed that 494 bridges failed during the years 1951 to 1988 as a result of hydraulic conditions, primarily due to scouring. So this last bullet is a very important bullet which reveals that post collapse of a bridge, lessons were learned by the authorities. The authorities took corrective steps, and they could identify also the concerns, and they also identified so many how many bridges collapsed due to scour and what precautions are to be taken in future. So with that, I come to the end of this particular presentation. This was, as I mentioned, my fourth presentation as in a series, and I just want to, before I open this floor for discussion, I just want to just recap what I did in last four lectures. The first lecture which I had given was related to recent advances in forensic structural engineering, basically giving a broad overview of what forensic structural engineering is all about, and why this subject is so important, and what all as a forensic structural engineering subject, what all you are supposed to learn, and how you are supposed to use it in your professional practice. The other three lectures, including the lecture today, I took three case studies, two for bridges and one for a roof structure, a collision. And what conclusions did I derive? I think the first lecture I said, I in the overview of the forensic structural engineering, I talked a bit about the ancient history of failures. I talked about what forensic structural engineering is, what are the origin of failures, what are the source of errors and cause of failures. I also talked about the failure education for students and practitioners. In the second lecture, in the I-35 highway bridge collapse, we learned what is the importance of quality control procedures for designing and proof checking of bridges. What are the importance of need to review any change that is proposed in bridge after it is in service, so that there is no overloading or there is no sort of reduction in the capacity. The importance of safety guidance with regard to the placement of construction load on bridges also was highlighted in this particular collapse. One of the attributes of the collapse was the placement of construction load on the bridge and need for inclusion of gazette plates in the bridge load rating guidance. This is what we learned in second lecture. In the third lecture on Hartford Civic Center Coliseum, we learned that we should not over rely on the computer analysis. This is not a good practice. There is always a need to check the computer results by a quick method, hand calculation methods. You must always find your own ways of quick checking so that you have a control over the analysis that you do in computer. Then we also learned that qualified and competent structural engineers should be there at the site during construction to coordinate between the designer and the contractor. In this particular failure, the structural engineer at site was missing, and that resulted in miscommunication between the designer and the engineer construction manager.